Good morning, everyone, and welcome to a new webinar organized by the Thematic Partnership S3P on Traceability and Big Data in the Agri-Food Value Chain. My name is María José Valverde, and I'm Technical Advisor of this partnership, coordinated by the Regional Ministry of Agriculture, Livestock, Fisheries and Sustainable Development of Andalusia. First of all, our coordinator, Judith Anda, apologizes not to be here with us, as she is attending an urgent meeting. After the summer break, we start again with the monthly cycle of webinars. This time, I'm very happy of presenting our speakers that come from one of the associated members of our partnership. As you may know, traceability and big data is not only a partnership of 22 regions. We also have 12 associated members, and one of them comes from Portugal, ISQ Group, company of our today's speakers, Joao Ribau and Bruno Ferreira. Today, we are going to speak about an interesting topic that is very important for the future of the agriculture and the farmers in their process of digital transformation. I'm speaking about new trends on driving the herd observation with artificial intelligence. Briefly, I'm going to speak about a short bio of our speakers. Joao Ribau is the head of intelligence and digital systems in the Research and Development Unit of ISQ Portugal. His Ph.D. degree in mechanical engineering with focus on optimization and decision techniques. Joao is responsible for coordinating research in several European and national programs like Horizon 2020, LIFE, etc., with focus on artificial intelligence, IoT, and Industry 4.0. Bruno Ferreira is research at ISQ at the Intelligence and Digital Systems in the Research and Development Unit. He is also a PhD student in Engineering and Industrial Management, and he holds degrees in Electronics and Informatics Engineering. Currently, he is responsible for research on artificial intelligence techniques applied to herd observation data, including machine learning models applied to satellite data, herd observation sources, and data analysis, among others. Finally, the presentation will last about 40 minutes, and after we will open questions and answer time. Until that moment, please ensure your microphone is muted. And in case you have any question, you can use the chat, and Joao and Bruno will answer during the Q&A session. Joao and Bruno, the floor is yours.
Thank you very much. First of all, good morning to all of the participants. And thank you also for the nice presentation from our side. I think that this presentation that me and Bruno prepared is not super technical, detailed, but it's also not too much generic. I hope that also you enjoy and especially not get bored, but most of all, we will try to focus on several topics that are concerned to Earth observation, artificial intelligence, and what we can extract from these two topics. And obviously, the Q&A session hope that will bring good discussions. But anyway, for any details, me and Bruno are available. Here are our emails, so please be free to get in contact with us for any question at all, any discussion. So we'll be happy to answer any email. So just to get started, so we will try to see what really Earth observation is, what applications can we get from Earth observation technologies, and how artificial intelligence enter this topic, why we need artificial intelligence and which techniques we may need from artificial intelligence, and obviously see some applications of that in Earth observation, finalizing with some conclusive remarks before the Q&A session. So, what is Earth observation? Well, Earth observation is a remote sensing technique to collect information on the planet Earth, and can be done not only by satellite, but for any other remote device, from drones, aircrafts, although we are more and more using satellites every day. More satellites are up in the space and are equipped with more sensors. And all the information that we can extract from these remote sensing techniques give us information on the Earth about its physical, chemical, biological, and anthropogenic events, which can be used in several subjects, from oceanographic, agronomy, climatology, meteorological events, ecology and environment, man-made infrastructures. Well, more and more subjects are appearing every day. And from all of this information, perhaps the most important factors that we must consider concerning the sensors that equip the satellites are the resolution, and the resolution means at least spectral resolution, which describes the ability of the equipped sensors to detect signals from different wavelength intervals. The spatial resolution, that, well, as the name indicates, means how good can we see in a specific area. It's like imagining a pixel in our television, in our screen. It's how good can we see in the smallest dot that we can determine in a specific area. I will briefly show some examples. And finally, the temporal resolution, which means which frequency can we get the image or the signal from the same area on the Earth. And we have several satellites, several sensors, and the combination of which each of these give us information that can be useful in several areas. I will just name some examples. For instance, the climate measurements, the climate change measurements here in this figure are placed in a zone where we perhaps need less temporal and less spatial resolution because, well, the climate change does not have very high variation in space and geography, and neither on a temporal matter. So it is very, or at least reasonable, slowly. So, but what we need a very good spectral resolution, because this gives us more information of what is actually visible. So we can calculate good indicators for the climate change seen beyond the visible spectrum. I will briefly show a little bit more on that. On the other hand, geological and geography, topography matters actually don't care really much on temporal and on spectral resolution. Well, obviously depend on the case study, but the spatial resolution, it's very important. The precision on the spatial area, it is very important. And another good example is emergency response, such as disasters and, for instance, floods. We need high temporal resolution, high spatial resolution, but actually the spectral resolution, it's not so much needed. And what I'm talking about, so spectral resolution, we can see here an example of the wavelength that actually matters for the subject. We have the visible wavelength to the human eye, but we have several others like shortwave, infrared. We have sensors in satellites that can capture indicators like seeing clouds, vapor, emissions. That's not on the visible human eye. And each wavelength has some matter, a special matter depending on the subject. And we have sensors equipped in the satellite that can be, well, use a single spectral resolution or multispectral resolution that gives us a lot more of capability from these sensors. Well, the spatial resolution, I think it speaks for itself. We can see here the comparison of the 250 meters resolution in the first square, and the last one 30 centimeters resolution. It's actually how good can we see determine the differences in spatial area that we want to take the information. Depending on the subject, this can be important or not. So actually depends on the examples that will perhaps show a little bit later. And we can see here the importance of this. And the temporal resolution, well, it depends on the time that the satellites pass through the same area as I spoke before. And this obviously gives some implications on the frequency of the images that we can take. We can have satellites that can give us the image like in 1 hour, differences in 1 hour, or satellites that take some years taking the same area. Obviously, for instance, in climate change, we don't need actually 1 hour images, but perhaps in emergency response, we may need some of that. And the differences between all of these sensors obviously give us different information, but also if we want to work with this data, there are some costs. There are satellites that can give us some public data sets at zero cost, but obviously if we are speaking about multispectral data, infrared, good temporal resolution, good spatial resolution, we can reach 25 euros per square kilometer on public data sets, and obviously you can get a little bit much higher depending on how good we want our resolution to be. Some examples here of the use of this data, the use of this resolution. For instance, in agriculture, we can see here the bright red that indicates photosynthesis, active vegetation, indicates cultures in Italy. It's very different from the area around here. It's reasonably easy to see where the fields have crops or not. Obviously, we have here reasonable spatial resolution around perhaps 10 meters. Here in Vietnam, we can see here the rice fields, the squares, the rectangles here indicate rice fields, in the bright color, the purple color here indicates some changes from the last data acquisitions. We can put some layers of different acquisitions and see the evolution of the fields or where most activity occurred. Another example, as I spoke before, some disasters we can see here in Spain, in Portugal, where fires were more active in this burned area. It's pretty easy to see. Here, obviously, we don't need much spatial resolution, neither spectral, but it's pretty easy to see, unfortunately. Flooding in Iraq, well, it's easy to see here in bright red where the floods occur. In dark, we can see the water due to the for reflecting data. It turns black. But this water here, it's like it's usual, stays here. It's river, but on red, it's identified the differences on the water, so it's indicating some floods, and it's several miles into the cities. It's a disaster. Concerning to human activity, we can see some examples here of the rectangles on a lithium recovery plant from the salt Rhine in Bolivia. Deforestation, satellites are used increasingly in trying to detect human activity in deforestation. It's one of the activities that's most concerning, and using satellite data is very useful mostly because they are in remote areas and we cannot reach that area very easily. So satellite data can see some changes in the terrain, and here it's very easy to see the pattern, the radial patterns due to deforestation. In the rectangles up there, the agriculture sector moving on the forests. So it's a good example of the use of Earth observation also. Emissions, detect emissions, in this case nitrogen dioxide over Europe. We can see here the great focus on Europe. We can see in Spain, Madrid, Barcelona, in Portugal, Porto, and Lisbon. These emissions are mostly due to traffic, to transport. So big cities have this problem mostly. And here, it's another interesting application of Earth observation. It is to detect fishing activities, analysis, and an illegal activity, well, depending obviously on the data that we have on the geography in each country, but we can detect this activity. And here, it's an example where the temporal resolution really matters, because we are focusing moving objects. The Earth observation research evolution is okay. We have more satellites, we have more data, and how is the research doing? Well, the research is increasing also. Researchers from companies and research institutions are looking at this data and seeing very useful applications that obviously need some research. Also, some of this data cannot be used like directly. We must research a little bit more on that and explore new methods to process the data. We will see a little bit later. And how about Earth observation? We can see here an orange full line, but Earth observation combined with machine learning methods, so processing method, exploration method of Earth observation, that machine learning, we can see here like artificial intelligence, not exactly, but yes, we can do that. And this mixed by sector for agriculture, climate, forest, marine habitats, mining, and the renewable energies. All of these are increasing, which shows that research is looking at Earth observation, artificial intelligence as a good tool to put on service of these sectors, like the examples that I've shown before. Now, how can we extract data? How can this work? Getting a little bit more technical, where we'll divide this in three main areas. The main area, we call it like raw data, data acquisition. What really matters is to get the data from the satellite's sensors. Obviously, this data is not only collected by the satellite, but must be transmitted to us here on the planet Earth. And obviously, the data must be believable and calibrated. If validated, even better. And after that, we pass to the data management. And inside data management, we have the collection and storage infrastructure, because we are talking about a lot of data. We have several data visualization tools, and we have several processing models and algorithms that allow us to see actually this data transformed to images, some useful images as we see before. And besides that, if we mix with this data some models, not only artificial intelligence models, but also earth, biological, geophysical, chemical models, depending on what we want to see on Earth. Mixing this with Earth observation data from the satellites, we can have lots and lots of good indicators, calculated indexes, predictive insights, and see beyond what is extracted from the satellites. We can reach lots of information from instance. I can give you a very brief example of some data that we can extract directly from the satellite in stage 1 and 2. It can be like detecting water stress in agriculture or detecting some crops area in large fields. But then if we want to see detect a plague or a disease or some issue that is affecting a specific culture, we need to put some phytosanitary models, some AI to analyze this data, bring us some indexes like photosynthesis, reflectance, and pigment indexes, some vegetation indexes from this exploration models to see beyond what is gathered in satellites. Well, this is almost the same thing, but organized in another way. I found this picture in a report, a strategic plan for Earth observation in Netherlands, and I found that it's quite complete. So we see the data on Earth, we gather the data not only by satellite, but we can obviously use, and we must complete the satellite data with in situ sensors. And all of this data processed by algorithms, we can see a little bit what is going on the data. But if we want to find some patterns on the data, some calculations that we cannot see directly in the data, yes, we can apply some more advanced models and see beyond that. Obviously, always validating with in situ data, not only to validate the algorithms applied, but also to validate the data in this feeds in like an ecosystem. We must Earth observation by satellite. It's not per se the method. It must be complemented with in situ measurements in order to be more precise. So I think, Bruno, you may take the controls.
Okay. So following the section before, we can state that Earth observation is creating or producing more data from more data sources and with more quality. And due to that, it is necessary to apply techniques to analyze this amount of data. And it is here that artificial intelligence, which refers to the capability of a machine to emulate intelligent human behavior, has a significant role. Several projects and studies prove the potential of artificial intelligence techniques applied to Earth observation data, mainly due to their unique characteristics for classification, modeling, and forecasting. So the combination of artificial intelligence and Earth observation data allow to monitor a specific characteristic or area through the repeatedly acquisition of data by different Earth observation data sources. This data is then structured and stored in a database, and for the predictive analysis, the data previously stored and processed and indices such as vegetation indexes are calculated And then artificial intelligence technique is applied to this data, and the results are produced. These results can be very useful. For example, to monitor soil conditions or to detect some disease. The first steps of artificial intelligence were taken in the 40s, and the field has been evolving since that. The figure at the right presents some of the most important milestones of the artificial intelligence history. Where more recently, we can see here, we have the self-driving cars. Due to its long history and wide range of applications, artificial intelligence was divided in several subdomains, such as robotic computer vision, natural language processing, and machine learning. But we need to answer why do we need artificial intelligence now? And some factors that contribute for that are the increased amount of data and processing power, our connected globe, which allow us to share information more easily. Today we have several softwares and data sources that are open source, and the fact that researchers have made significant advances in several aspects of artificial intelligence. The spectrum of artificial intelligence application over automated intelligence systems, which are systems to automatically complete repeated tasks that requires intelligence, assisted intelligence systems to reveal patterns in data, augmented intelligence systems to help people to simulate different scenarios, and autonomous intelligence systems to automate decision-making without human intervention. Despite the benefits of artificial intelligence, we also have some risks at different levels. In performance, we have risks, for example, of errors. In security, risks of cyber intrusion. In control, the inability to control malevolent artificial intelligence. Ethical, the lack of values. Economic, the reputation. And societal, the risk of autonomous weapons proliferation. So, as we saw before, machine learning is a subdomain of artificial intelligence, where the study and development of algorithms play a major role. The main goal of machine learning is to provide to machines the ability to learn from data without being explicitly programmed for that. And today, the popularity of machine learning algorithms originated several different domains, such as data mining, natural language processing, or deep learning. And it is applied to several fields as well, like agriculture, or climate, or disaster. The machine learning also has different categories according to its learning process. The most important ones, or the most well-known ones, are the supervised learning and unsupervised. In supervised learning, it is necessary to have all the observations in the training data classified. In this example here, the training data was labeled as cat, and the data was provided to the algorithm. And after the learning process, the algorithm was able to distinguish cats from non-cats. The types of supervised learning problems are classification and regression. The unsupervised learning is the opposite of the supervised, because it is necessary to have data without the classification or unlabeled data. In the example here, the training data, which has unlabeled images of cats and dogs, was provided to the algorithm. And after the learning process, the algorithm was able to distinguish the cats from dogs by grouping them accordingly to their similarity. The types of unsupervised learning problems can be clustering or anomaly detection. In addition to supervised and unsupervised learning, we also have semi-supervised, which falls between supervised and unsupervised because it needs labeled and unlabeled data. So the general process of machine learning consists in two main steps: the training, where we apply algorithms to historic data. This historic data means that this data was already classified and structured. And the combination of this data and the machine learning techniques will provide a predictive model. And we have the scoring phase here below. And here the new data is giving to the predictive model, which is the result of the training phase. And it will produce the predictions or the classifications. Learning is a subdomain of machine learning, and its algorithms are called artificial neural network because they were inspired by the architecture of the biological neural networks in the brain. Here, the learning process is similar to humans, where we learn from experience and by trying to improve our results. Some of the most well-known deep learning algorithms, as well as their reference, are present in this table. And these algorithms have achieved great results in several different applications, such as visual data processing, natural language processing, speech audio processing. Similarly to the graph of Earth observation, here this graph presents the number of publications containing the expression artificial intelligence, machine learning, or deep learning per year on Google Scholar. And from this graph, we can conclude that until 2009, artificial intelligence was the most relevant topic. In the last few years, artificial intelligence and machine learning are decreasing the number of publications, while deep learning is increasing. And the most relevant topic since 2012 is machine learning. As we saw before, artificial intelligence and Earth observation have been applied to several subjects. And the oceans are one of them. And here, the combination of artificial intelligence and Earth observation can help to prevent things such overfishing or monitoring the pollution or mapping species. In water security, artificial intelligence and Earth observation can help to predict water stress, illegal discharges, and water quality. On climate, can help by monitoring crops, urban planning, and urban emissions monitoring. On biodiversity and conservation, they can help by predicting disease, preventing the deforestation, and species identification. On air quality, they can help by giving air quality alerts or pollution monitoring. And on weather and disasters, they help by predicting and modeling the climate, for example. And lastly, as we can see in this figure, Earth observation can be very useful to monitor the sustainable development goals by measure or monitoring their indicators here. The most relevant indicators are the population distribution and cities and infrastructures mapping. And on the other hand, the sustainable development goals that benefit from all the Earth observation indicators are zero hunger, clean water and sanitation, climate action, life below water, partnerships for the goals. As a conclusion, we can state that Earth observation is increasing sensor quality and quantity. is considered an important big data source. It can help us to reduce time and cost associated to the traditional data acquisition, while the artificial intelligence is applied to several fields with state-of-art results, has more capacity to analyze data, search hidden patterns, reduce the time of data analysis, and the combination of these two, the Earth observation and artificial intelligence, allow us to monitor and understand the Earth ecosystem, sustainable development goals, humanitarian and pollution initiatives, and specific fields problems. So, thank you all. And if you have any questions, just let us know.
Thank you, Joao and Bruno, for giving us the latest trends and the different uses on Earth observation with artificial intelligence. I agree that it's very important to bet about the use of these technologies for being more capable and faster to deal with the big amounts of data and take better decisions on agriculture, water, forestry in many fields, as you have explained. We can move quickly to the questions and answer time. We are going to start with a couple of questions that you have written during the presentation in the chat, and after that, please feel free to open your microphone and ask questions to our speakers or give us your opinion. We are going to start with the Lucia Castro questions, and she said, any examples of identifying forest areas, species, years of growth, whether cultivated or wild, etc.? Could a forest census be created? What would be required regarding cost and infrastructure?
Thank you. Yes, I think, first of all, I think the answer is yes. Obviously, depending, for instance, if we want to identify forest areas, it's reasonable, easy. If we want, or cultivated areas, but if we want to specify which species are we talking about, for instance, to build a forest census, I do believe that it's not enough to get some raw data from census, and we do need some more calculations on vegetation indexes and other kinds of things like carotenoid identification, photosynthetic indexes. And I do believe that we need to put some in situ sensors or get someone to validate this data in order to correlate the data that we gathered from the satellites and, validate the data that it's actually there. And as Bruno showed in a slide, for instance, just to put some more technical focus on this. So we are speaking on the first layer, and if we get this, we get validated data. We feed this to a machine learning model, and potentially it can identify as different species. Obviously, in what concerns to cost, we are talking about, if we want identification of species, we are talking about probably multispectral sensors. So the satellite data will have some costs. I don't know if we really needed the most expensive ones like 25 euros for square kilometer, or if we will manage to do the same things with some with less powerful sensors. Obviously, that depends on the species. We had a project where we try to identify a disease in olive crops. It's it was not entirely focused on Xylella fastidiosa, but it's a disease similar to, well, it's a branch of this disease, and we do not entirely focus on satellite data. We really need in situ sensors, and more than that, it would be better in this kind of disease, because, for instance, this kind of disease has lots of problems like symptomatic activity, and the symptoms that can be mixed up with other things like lack of water or nutrients. And we need other models to complement this data. For instance, measuring insects occurrences, climate, weather, and all of these mix, we can get much more. It's like as much data as we can get. It's good for building a good model, and it's not only focused on Earth observation data and AI, but it's focused on Earth observation, AI, and if we can, other and non-models. So in order to detect different diseases, different animals, different vegetation types. Bruno, do I miss something? Do you have something to complement, or I talked a little bit of all? What do you think?
No, I don't have nothing to add to your response. So from you, we can move on.
Okay, thank you. So I hope to answer. I hope I could answer the question.
Okay, so we are moved to the following question, done by Agustin. He said, during the presentation, you are talking several times about the spatial resolution of satellites. There is a specific problem with this in woody crops like olive or citrus. How do you think that the measurement of the index could be improved remotely without resorting to drone?
Bruno, perhaps you can have some exploration about different indexes and mixing some data. I don't know.
So, what do you think of measurements of index? Yeah, so several vegetation index can be calculated, but we need to pay attention to the spectral resolution, because some satellites don't allow us to calculate some specific indexes. And I think that in order to answer your second question, I think that the satellites, or the quality of sensors on satellites, are increasing very quickly. And they are now creating constellations of satellites in order to have an inferior temporal resolution. So I don't think that we need drones for this, because we had a project called InteliCROP, and we tried to predict some phytosanitary issues like Xylella. And for that, we used Sentinel-2, which has a spatial resolution of 10 meters, 20 meters, and 60 meters. So it's not the best resolution available, but it's free, and we've done our job with those kinds of resolutions. So I don't know if it is necessary to use drones.
Yeah, just to complement that, in speaking about the InteliCROP project, the key was to get validated data. And if we cross in situ data with positive and negative measurements for this kind of the disease, we can actually train a good model to do that. And more than that, if we mix that with some ecosystem or biological know-how, we can get much further, because it's obviously, if we use a drone to get better images, better data, it can be good for some specific case studies, but the good thing about Earth observation using satellites is to get some remote areas and very large areas. And using drones sometimes it's not so viable to do that. So the key here is to have other layers of data beyond this kind of sensors. I do believe so. Yeah.
Yes, and we need to highlight the difficulty of acquiring historic data, because it was our biggest problem, bigger problem.
Yeah.
So.
Okay, let's move to the next question now. Sorry. Cecilia Gañán de Molina says, thank you, Joao and Bruno. Really interesting presentation. I agree with Cecilia. Really interesting presentation and really fascinating images. Bruno, could you explain a little bit more in detail how artificial intelligence is supporting the monitoring of the Sustainable Development Goals?
Yes. So if we look only to the data, we can see that we need techniques to analyze this amount of data, because it's a lot of data and lots of attributes, and we need to process this data or analyze this data as faster as we can. So due to that, we need these kinds of techniques. But we can also speak from the developments that artificial intelligence brings to us, like the autonomous or self-driving vehicles, like, I don't know, like drones. And these drones can help us to collect more data, and some of the technological developments can increase the frequency of the data, the quality of the data, makes more easy to validate the data. I don't know if I answer your question, but João, I don't know if you...
Yeah, I can complement a little bit on that. Well, each case is different. I can give some examples on of some projects that we may have. For instance, on agriculture sector, that I like. I'm always speaking on that sector. But the agriculture sector, we can use artificial intelligence to detect some patterns in data that indicate us in a specific large area where the water is lacking a little bit more, where exists more water stress. And this is important in water allocation in fields, because obviously the crops, if the crops change, the farmers know the sustainable farmers, the good farmers know which kind of nutrients and how much water do they really need to put on that crop in order to, obviously, in this case, save water. But if all the crops are the same, but obviously the fields, the geography, the topography, it differs a little bit and creates micro climates, all the crop can have different behaviors and can have different water stress issues. And this kind of like the vegetation indexes that we can read from Earth observation, and seeing these kind of patterns with AI teaches, okay, in this field we must put some water, or we can put some more irrigation efforts in this area in order to save water, and we should not irrigate in the same way all the fields. The water allocation is a very good example because it's an increasingly interesting topic nowadays. Example I can give you, it's another project where we are working. It's on deep sea mining, and the key here is trying to not only detect mineral areas in deep sea using Earth observation, and we do that trying to find some data that is a good indicator in geological terms, and we do that using machine learning because data it's a lot, so it's a matter of identifying patterns in the data that can indicate us something, and in this case the occurrence of mineral resources. But the key here is trying to find that, but on areas or in a way that it's not harmful for ecosystems, because, well, deep sea mining is a very stressful activity, and this is very important. Trying, okay, if we're gonna do that, we must do that, but in a way, in an area where the ecosystem is not harmed. It's like trying to detect illegal fishing. We know the areas, we know when or how, or where we can do that or not. So it's some sort of that mixed with the calculation of some indexes. Two good examples, perhaps, or simpler examples.
Thank you very much. Thank you.
Thank you.
Thank you, Cecilia, Bruno, and Joao. And now we move to Agustin again, that says that last year I did a master thesis on citrus harvest prediction with Sentinel-2. I used simple algorithms like random forest or logistic regression, since they gave me better results since I did not have a large sample. I would like to ask, from your point of view, what do you think is the best workflow and the best algorithms for this type of tasks that can be very useful to the farmer and the value chain? Thank you very much for the interesting presentation.
So I think that the most important thing is to acquire historic data concerning several features or characteristics of the study area. This is the essential part. And then we can try to apply several different algorithms. In InteliCROP, I used 16 algorithms. I compared the 16 algorithms. Then I selected the best 4, and then I optimized these 4 algorithms, and I choose the most accurate one. And it was, if I don't want to say something wrong, but I think it was random forest or extra trees. But if you want to improve your results in a quick way, I think that you can optimize your algorithms and try different approaches. You can use regression technique, or you can use multiple classification techniques and do a thing called RECA, which is regression for or classification for regression. And here we use more than one classification algorithms, and we do the average between the outputs of these two. And in InteliCROP, we also have the problem that we didn't have too much data, but we could prove our point. And now we will we will have the second part of the project, which is a use case. So we will use that on a specific end user. But I think that the workflow is that you need to gather as much as data as you can, and then try several different algorithms, optimize them, compare them, and then you have the best results possible for your data, essentially. João, if you want to
no, it is a very good question. I just want to complement that with it's not demotivating, but it's like that. It's not good to say, well, this algorithm is the best. Well, this is always wrong to say that. That depends on the features that we have, and obviously on the objectives that we want to find on the data, and obviously also if you have good validated data, a lot or not. So it is not demotivating, but yes, we have to try different algorithms. In one case study, one can be greater than the other. It is a mix of trying all of the things, but it's just like that. Fortunately, nowadays, most of the algorithms are very well evolved, and we can try different ones without, well, building them from scratch. So I think that's the best answer, like Bruno said.
Okay, I think that we don't have more questions. If somebody of you want to open the microphone and comment something or type it in a question in the chat, we can wait for a while because it's midday. So if not, we can finish the session. Well, I think that there is not more questions, so I want to thank again to Joao, Ribau, and Bruno Ferreira for their availability and their great presentation. Well, as we said, the use of artificial intelligence in the Earth observation is a very important topic for the Traceability and Big Data Partnership, and I'm sure today we have learned more about it. Also, thanks to all the participants who have joined today and that have collaborated with your interesting questions. Have a nice day and bye. We will stay here the next week with another webinar. Thank you.
Well, thank you very much. I really enjoy it also, and please be free to contact us for any details. We are available for that, and I'm very happy to participate in this presentation. Thank you very much
thank you all
for your questions. Yeah, it was very, very good.
Thank you.
Bye. Thank you.
Thank you.
Thank you. Thank you. Bye. Thank you.